The trajectory calculations are unstable at peak velocity.
We must adjust the gimbal angles immediately, or it will fail.
Late autumn 1945. The war in Europe has ended, but its machines are still humming. Inside a vast American industrial hall, the air smells of oil and hot metal. Overhead lights burn steadily, illuminating long production lines that stretch farther than the eye can easily follow. Steel frames move forward on rails. Engines arrive in crates. Components are bolted, wired, tested, and passed onward without ceremony. A small group of German engineers stands off to the side. They wear civilian coats now. Their notebooks are thin. Their faces are still. Only months earlier, they worked at Peenemünde and Middelwerk, where rockets were assembled almost by hand. Every V-2 was treated as a singular object. Tuned, adjusted, argued over, delayed. Here, no one pauses. A rocket motor is not admired. It is counted. A supervisor checks a clipboard. A whistle sounds. Another unit moves forward. What unsettles the observers is not that America has rockets. Germany had proven that already. It is the speed, the repetition, the calm certainty that tomorrow will bring more. Identical, replaceable, unstoppable. For the first time, the engineers understand that the future of warfare will not belong to those who build the most advanced weapon, but to those who can build it endlessly. And that realization can only be understood by returning to how the world arrived at this moment. Long before the assembly lines of America came into view, Germany's rocket story had already reached its highest and most tragic expression. In the early 1930s, rocketry in Germany was not yet a weapon. It was an obsession. Amateur societies, university engineers, and former artillery officers gathered around test stands and chalkboards, driven by mathematics rather than strategy. Among them was a young Wernher von Braun, whose fascination with spaceflight coexisted uneasily with the political reality of a rearming state. The German army recognized potential early. By 1932, the Reichswehr was quietly funding liquid-fueled rocket experiments, seeing in them a way around the restrictions of the Treaty of Versailles. Conventional artillery was limited. Rockets were not. What began as theoretical research soon became institutional. Peenemünde, established on the Baltic coast in 1936, was the physical embodiment of this philosophy. It was isolated, expansive, and secretive. There, under the technical direction of von Braun and the military command of General Walter Dornberger, Germany concentrated its most advanced rocket mines in one place. Engineers lived near their test stands. Failures were analyzed in detail. Successes were celebrated cautiously. Each launch was an event. The V-2 rocket, officially the A-4, was not designed for ease of production. It was designed for performance. Standing over 14 meters tall, powered by liquid oxygen and ethanol, guided by primitive onboard gyroscopes, it was the first human-made object to cross the boundary of space. But every technological leap carried a cost. The V-2 was complex to the point of fragility. Its turbo pumps required precision machining. Its fuel systems demanded careful calibration. Its guidance instruments were sensitive to vibration, temperature, and assembly errors. Small deviations could cause catastrophic failure. As a result, rockets were assembled with an almost artisanal mentality. Skilled technicians adjusted components by hand. Engineers signed off on individual vehicles. There was no illusion of interchangeability. This approach reflected German engineering culture at the time. Precision was valued over quantity, excellence over throughput. A weapon was something perfected, not multiplied. The Luftwaffe followed the same logic with its aircraft designs. Technically advanced, often superior in performance, but increasingly difficult to produce and maintain as the war expanded. By 1943, that philosophy collided with reality. Germany was losing the air war. Allied bombers struck industrial centers by day and night. Fuel shortages spread. Skilled labor vanished into the front lines. Peenemünde itself was attacked in August 1943, forcing the V-2 program underground to the middleware facility near Nordhausen. Their production continued in tunnels carved into mountains, using forced labor under brutal conditions. Even then, the rockets did not become simple. Each V-2 still required enormous human attention. Production numbers increased, but never enough. Hundreds were built. Thousands were hoped for. Hitler saw the weapon as a potential war-turner, but its impact was psychological rather than strategic. The rockets arrived too late, in too few numbers, and at too high a cost. By 1944, Germany's leadership was desperate. Conventional forces were collapsing on multiple fronts. Cities burned. The V-2 became less a weapon of victory and more a symbol of defiance, a final assertion of technological brilliance in the face of material exhaustion. Yet, even as the Reich strained to produce a few dozen rockets per month, across the Atlantic, a different kind of war effort was unfolding. One that treated machines not as masterpieces, but as products. And it was this difference, quiet, structural, and profound, that would soon redefine the future of rocketry itself. When the United States entered the war in December 1941, it did so with an advantage that was not immediately visible on any battlefield. America's greatest weapon was not a tank, a bomber, or a battleship. It was an industrial system already built for scale. For decades, American manufacturing had been shaped by Fordism, the philosophy that complex machines could be broken into standardized tasks, performed repeatedly by semi-skilled workers, using interchangeable parts. Henry Ford's moving assembly lines had transformed automobiles into consumer products. During wartime, that logic was repurposed without hesitation. By 1942, the transformation was total. Automobile plants became aircraft factories. Refrigerator companies produced machine guns. Shipyards along both coasts launched Liberty ships faster than German submarines could sink them. These vessels were not elegant. They were functional. And, most importantly, they were replaceable. This mindset shaped every American weapons program. Engineers were expected to design systems that could be built by the thousands, maintained by conscripts, and repaired in the field. If a component failed too often, it was redesigned. If a part could not be produced reliably, it was simplified. Perfection was secondary to continuity. The American aircraft industry demonstrated this most clearly. The B-24 Liberator was assembled in plants that resembled automotive factories more than traditional aircraft workshops. At Willow Run, a completed bomber rolled off the line every hour at peak production. No other nation approached this scale. Rocketry, however, remained peripheral during most of the war. The United States did not face the same constraints as Germany. It possessed long-range bombers. It controlled the seas. There was no urgent need for ballistic weapons. As a result, early American rocket research remained fragmented. Small programs existed. At the Jet Propulsion Laboratory in California, engineers focused on rocket-assisted takeoff units and experimental propulsion. The U.S. Army Ordnance Department explored solid-fuel rockets for artillery. The Navy developed air-to-ground rockets for aircraft. None of these efforts resembled Peenemünde. They were practical, limited, and deliberately cautious. Yet what the Americans lacked in advanced rocketry, they compensated for in infrastructure. Test ranges were expansive. Factories were adaptable. Supply chains stretched across a continent untouched by bombing. When a new weapon was approved, production could begin almost immediately. By 1944, this structural advantage was unmistakable. American factories were producing tens of thousands of aircraft, tanks, and vehicles every month. Training pipelines were standardized. Documentation was meticulous. Every component had a specification. Every specification had a tolerance. Every tolerance was enforced by process, not by individual judgment. This was not a culture of inspired engineering. It was a culture of managed engineering. As the war drew to a close, American intelligence agencies turned their attention to German technology. Reports from Europe described weapons that defied interception and reached the edge of space. The V-2 was understood not as a battlefield threat, but as a glimpse of a future domain. Operation Paperclip was born from that realization. In 1945, as Allied forces overran Germany, teams moved quickly to secure documents, hardware, and personnel associated with advanced weapons programs. German engineers were located, questioned, and transported. Entire rail cars of rocket components were shipped across the Atlantic. Test stands were dismantled and reassembled on American soil. When the first groups of German rocket specialists arrived in the United States, they entered a world that felt alien. Facilities were vast. Budgets were flexible. Production schedules were measured in quarters, not years. And surrounding all of it was an assumption that any successful design would not remain rare for long. For engineers raised in a culture of careful construction and individual mastery, this was the true shock. Not that America had acquired German rockets, but that it intended to make them ordinary. And as these two engineering philosophies collided, the consequences would soon become impossible to ignore. German rocketry emerged from a tradition that treated engineering as an intellectual pursuit. At Peenemünde, problems were solved by elite specialists. Decisions flowed upward to small circles of authority. A rocket was not merely assembled. It was interpreted. Each flaw demanded explanation. Each success demanded understanding. This culture produced brilliance. It also produced bottlenecks. The V-2's design assumed constant expert oversight. Tolerances were narrow. Components were sensitive. When something went wrong, production paused while engineers diagnosed causes. The system relied on mastery, not momentum. Knowledge lived in people, not processes. American engineering culture approached the same challenge from the opposite direction. The goal was not to understand every failure, but to reduce their impact. If one unit malfunctioned, another replaced it. If a process caused delays, the process, not the people, was redesigned. Skill was embedded into tooling, documentation, and workflow. In American factories, intelligence was distributed. A single worker did not need to grasp the whole system, only their task. Precision existed, but it was statistical, not personal. Variation was expected and controlled, not feared. To German engineers, this seemed reckless at first. How could such complexity survive without constant expert correction? Yet the answer became unavoidable. It survived because it was allowed to fail without consequence. The difference was not technical capability. It was philosophical. Germany built rockets as achievements. America built them as inventory. And in modern warfare, inventory outlasts achievement. For the German engineers brought to the United States, the shock was deeply personal. Many had entered rocketry as idealists. Some dreamed of spaceflight. Others sought technical challenge in a nation that revered engineers. War had distorted those ambitions, but pride in their work remained. They believed they belonged to an elite. In America, that identity quietly dissolved. They were no longer rare. They were specialists among thousands. Their designs were questioned by managers who did not share their academic background. Their assumptions were tested against cost sheets and delivery schedules. Decisions were made in meetings, not laboratories. What unsettled them most was not criticism. It was indifference. When American tests failed, the response was procedural. Data was logged. The next unit moved forward. There was no visible anguish, no sense of lost perfection. Failure was absorbed by the system. For engineers trained to treat each rocket as an extension of themselves, this was disorienting. Their work no longer carried individual fingerprints. It carried serial numbers. Yet adaptation followed. Slowly, reluctantly, many began to understand the freedom hidden within the system. No longer burdened with guarding perfection, they could focus on function. The machine, not the engineer, carried responsibility. This was the moment when admiration replaced disbelief. Not for American genius, but for American detachment. And that detachment would soon prove decisive. The V-2 was an innovation-heavy weapon. Nearly every subsystem represented a leap forward. Liquid-fueled propulsion, gyroscopic guidance, supersonic aerodynamics. These advances pushed the boundaries of what was possible, but also what was manageable. Innovation came at the cost of stability. American rocketry, after the war, took a different path. The first goal was not improvement, but replication. Designs were frozen early. Changes were discouraged unless failure rates demanded them. Performance gains were incremental. Reliability was paramount. Standardization became a form of technology in itself. Parts were redesigned to tolerate variation. Interfaces were simplified. Documentation expanded. A rocket no longer depended on ideal conditions. It was built to survive imperfect ones. This reduced peak performance, but increased operational certainty. German engineers recognized the trade-off immediately. The American approach would not produce the most advanced rocket fastest. It would produce the most usable rocket soonest, and in numbers. Innovation, they realized, was no longer a singular breakthrough. It was a cumulative process embedded in production lines. And as standardized rockets began to roll out one after another, the implications extended far beyond engineering, reaching into leadership, strategy, and morality itself. German rocket leadership during the war followed a rigid vertical structure. Authority flowed from the top down. Strategic decisions were concentrated among a small group of military and technical leaders. At Peenemünde, final judgment rested with figures like Dornberger and, ultimately, with political leadership in Berlin. This structure rewarded loyalty and technical excellence, but it discouraged flexibility. Once a design path was chosen, altering it required approval through layers of command. Production goals were often dictated by ideology rather than feasibility. When shortages emerged, responsibility rarely moved downward. It simply pressed harder. American leadership operated differently. In the United States, weapon development was managed as an industrial project rather than a national prestige symbol. Civilian managers, military officers, and engineers shared authority. Committees replaced directives. Timelines were adjusted openly. If a target could not be met, it was renegotiated rather than enforced. This did not eliminate pressure. It redistributed it. Responsibility in American programs was modular. A failed component did not indict the entire system. Managers focused on throughput, not personal blame. Leadership measured success by continuity, how long production could be sustained under stress. To German observers, this approach seemed dangerously casual, but its strength lay in resilience. When leadership adapted, the system followed. And as rockets became part of broader American planning, that adaptability would reshape how power itself was exercised. For German engineers and officers who survived the war, American production forced a reassessment of defeat. Many had believed Germany lost because it ran out of time, that its technology had been superior but incomplete. That victory was missed by months, not principles. The American assembly line dismantled that belief. Here was proof that technical brilliance alone was insufficient. The enemy had not merely matched innovation. It had absorbed it into a system that could outpace any individual achievement. This realization altered post-war German technical thinking. In both East and West Germany, industrial reconstruction emphasized process, discipline, and reliability. Engineering education shifted towards systems analysis and production engineering. The lesson was internalized quietly. The shock was not humiliation. It was clarity. The war had been decided not only by bombs and tanks, but by spreadsheets, logistics charts, and standardized components. Germany had built weapons that astonished. America had built a machine that endured. And for those who had once believed mastery lay in excellence alone, the revelation was irreversible. The moral weight of assembly line rocketry was subtle but profound. A hand-built weapon carries intimacy. Its creators know its strengths and flaws. Responsibility feels concentrated. A mass-produced weapon disperses that responsibility across thousands of hands, none of which see the whole. American industry did not invent this detachment, but it perfected it. When rockets became products, their consequences became abstract. Efficiency replaced reflection. A successful design was one that moved quickly from blueprint to storage. Destruction was no longer personal. It was statistical. German engineers understood this unease. Some had struggled with the moral implications of the V2 even as they built it. Yet the scale America introduced forced a deeper question. What happens when devastating power becomes routine? The answer was not immediate. It unfolded slowly as standardized rockets became missiles, and missiles became pillars of strategy rather than instruments of battle. And standing at the threshold of that future, between wartime experimentation and post-war reality, both nations approached a decisive moment. One where the assembly line would no longer support war. It would define it. In the spring of 1945, as Allied armies closed in on the remnants of the Third Reich, the future of rocketry quietly shifted hands. Operation Paperclip was not a single event. It was a process, methodical, bureaucratic, and deliberate. American intelligence units moved behind the front lines with lists of names, facility maps, and technical objectives. Their mission was not symbolic victory. It was acquisition. At Peenemünde, Nordhausen, and scattered research sites across Germany, documents were seized by the ton. Blueprints, test logs, propulsion data, guidance diagrams. Entire archives were packed into crates and shipped west. Rocket components followed. So did the people who understood them. Werner von Braun surrendered to American forces in Bavaria in May 1945. Within months, he and dozens of his colleagues were transported to the United States under military supervision. They were not treated as prisoners. They were treated as assets. Their first destination was Fort Bliss, Texas. Nearby, at White Sands Proving Ground in New Mexico, the desert stretched empty for hundreds of miles, ideal for experiments that could not fail publicly. The landscape was unfamiliar, but the purpose was clear. Between 1946 and 1951, the United States launched more than 60 V-2 rockets at White Sands, assembled from captured German components. These tests were not about combat readiness. They were about learning how rockets behave at altitude, how guidance systems drifted, how structures failed under stress. For the German engineers, this was familiar territory. What was not familiar was the pace. Launch schedules were ambitious. Failures were tolerated. Rockets exploded on the pad, veered off course, disintegrated mid-flight. Each incident generated data, not alarm. Test crews reset quickly. Another launch followed. Back at Fort Bliss, the engineers were exposed to something entirely new. Planning meetings focused not on whether a rocket could be built, but how many could be built and how quickly. American officers spoke in numbers. Monthly output, labor hours, material flow, concepts that had been peripheral in Germany now dominated discussion. Design reviews were accompanied by production forecasts. Performance was weighed against manufacturability from the beginning. In 1947, the United States Army initiated formal missile development programs. Unlike the V-2 effort, these were structured around future scale. The Corporal missile, America's first guided ballistic missile, was conceived not as an experimental marvel, but as a deployable system. Factories were selected before designs were finalized. Tooling considerations shaped geometry. Components were standardized across variants. The rocket was not yet elegant. It was achievable. German engineers watched prototypes move from drafting tables to production floors with unnerving speed. Facilities were repurposed almost overnight. Test articles appeared in rows rather than isolation. Documentation expanded into binders thicker than the rocket manuals they had written during the war. What unsettled them most was how early production was assumed. In Germany, a rocket earned replication only after perfection. In America, replication was the path to perfection. By 1950, this philosophy hardened into doctrine. Missile programs were no longer isolated research projects. They were embedded within the broader defense industrial complex. Contractors were evaluated on output as much as innovation. Deadlines mattered more than elegance. The desert launches continued. Each plume of fire carried not just thrust, but momentum, organizational, cultural, irreversible. The German engineers understood, even if few said aloud. They were no longer leading a revolution. They were contributing to one already underway. And as American rockets began shedding their German origins, something far more significant than technology was about to change. The turning point did not arrive with a single launch or announcement. It emerged quietly, across factory floors and drafting rooms, as American rockets stopped resembling German ones. The V-2 had been a technological peak, complex, temperamental, and extraordinary. Its successors in the United States would be something else entirely. By the early 1950s, the U.S. Army's Redstone program began to take shape at Redstone Arsenal in Huntsville, Alabama. Wernher von Braun and his team were present, but they no longer dictated the rules. The rocket they were building carried familiar DNA, yet it was reshaped by American priorities from its foundation. Redstone was designed to be built repeatedly. Its structure was simplified. Its guidance systems were more accessible. Components were arranged to ease inspection and replacement. The rocket accepted compromises that German engineers once would have rejected outright. And it worked. Parallel programs reinforced the shift. The Corporal missile moved from experimental deployment towards standardized production. Solid-fuel rocket systems expanded rapidly, favored for their storage stability and ease of manufacture. Each program reflected the same assumption. Rockets were no longer rare instruments. They were inventory. The psychological break came not with admiration, but with redundancy. German engineers began to see American rockets treated as expendable. Test vehicles were stacked outdoors. Units were scrapped without ceremony. Failed components were replaced rather than repaired. This was unthinkable in wartime Germany, where every rocket represented irreplaceable effort. Here, a failed missile was a data point. Production schedules tightened. Assembly lines refined their rhythms. Workers who had never studied rocketry assembled missile sections using jigs and templates that encoded expertise into metal and motion. Knowledge moved from minds into machinery. This was the moment Germany's technological edge finally collapsed, not in capability, but in relevance. The future belonged to systems that could be scaled, maintained, and replaced under pressure. The American approach did not eliminate innovation. It subordinated it to continuity. By the mid-1950s, the implications were unmistakable. Missiles were entering service not as wonders, but as tools. Strategic planning assumed their availability. Doctrine evolved around their presence. The age of singular weapons ended. For the German engineers, the realization was complete. Their early brilliance had ignited the field, but it was America that defined its direction. There were no speeches, no acknowledgments, just the steady movement of rockets along factory floors, towards storage depots and test ranges, counted by clerks rather than celebrated by scientists. The silence that followed was not defeat. It was absorption. And from that silence, a new era of warfare emerged, one whose consequences would echo far beyond the deserts where it first took shape. By the early 1950s, the transformation was complete. Rocketry had crossed a threshold, from experimental weaponry to a permanent pillar of military power. The immediate consequence was strategic. Missiles altered how nations thought about distance, warning time, and retaliation. Unlike aircraft, rockets did not require air superiority. Unlike artillery, they did not depend on proximity. Their value lay not only in destruction, but in certainty. If launched, they would arrive. American planners absorbed this lesson quickly. Production numbers mattered more than individual performance. A missile force was judged by readiness rates, stockpile size, and reliability under storage. The language of warfare shifted. Discussions centered on deployment cycles, maintenance schedules, and replacement capacity. This mindset contrasted sharply with Germany's wartime experience. The V-2 had been deployed as a terror weapon, dramatic, unpredictable, and strategically isolated. American missiles were integrated from the outset into broader planning frameworks. They were not symbols. They were infrastructure. The scale reflected this shift. Where Germany struggled to produce thousands of rockets under bombing and material collapse, the United States planned for sustained output in peacetime conditions. Factories were protected, labor was trained, and supply chains stabilized. Production became routine. Numbers tell part of the story. By the mid-1950s, American missile programs were producing at rates that would have been inconceivable at middle work. Failures still occurred, but they no longer threatened the program itself. Redundancy absorbed loss. Inventory replaced scarcity. This industrial confidence shaped the early Cold War. Missiles became tools of deterrence rather than desperation. Their existence altered diplomacy, forcing adversaries to consider not just battlefield outcomes, but national survival. The assembly line, once associated with civilian abundance, now underwrote strategic stability. For the former German engineers, this was perhaps the most unsettling consequence. Their work had helped open a door, but what passed through it was no longer under their control. Rocketry had escaped the laboratory entirely. The shift also influenced how wars would be fought or avoided. Mass-produced missiles reduced reliance on conventional escalation. They compressed decision time. They rewarded preparedness over improvisation. Warfare became less about maneuver and more about posture. Yet beneath the statistics and doctrines lay a quieter aftermath. The realization that technological advantage no longer depended on singular genius, but on organizational endurance. That the decisive factor was not who invented first, but who sustained longest. This lesson did not remain confined to rocketry. It spread across military planning, industrial policy, and technological development. Systems thinking replaced heroic engineering. Processes eclipsed personalities. And as the world adjusted to this new reality, the human dimension of that transformation, those who had built, adapted, and lived through it, remained unfinished. Their story would continue beyond strategy and numbers, into legacy, memory, and consequence. As the strategic landscape settled into the rigid geometry of the Cold War, the human legacy of this transformation quietly unfolded inside laboratories, offices, and classrooms across the United States. The German engineers who had once stood apart became woven into the American system. Many remained at Redstone Arsenal and other research centers, contributing to missile refinement, propulsion research, and eventually space exploration. Their expertise did not disappear, it was redistributed. Bound by contracts and oversight, they learned to work within structures that valued schedules as much as insight. Over time, the distinction between German and American approaches blurred. Younger engineers trained under standardized systems absorbed lessons from both traditions. Precision was preserved, but no longer fetishized. Innovation survived, but only when it could be scaled. The missiles themselves continued to evolve. Redstone led to Jupiter. Jupiter to longer-range systems. Solid fuel technology matured, enabling rapid deployment and long-term storage. Each step reinforced the central principle, reliability through repetition. Yet the psychological impact lingered. For those who had built the V2, there remained a sense of loss. Not for Germany's defeat, but for a way of working that had vanished. The intimate relationship between engineer and machine was replaced by distance. The weapon became abstract. This abstraction carried consequences. As missile forces grew, their existence reshaped political behavior. Crises were managed under the shadow of weapons that could not be recalled once launched. Decisions were compressed into minutes. The assembly line had not merely changed production. It had altered time itself. Public awareness lagged behind reality. Rockets were hidden behind fences and classifications. Their presence was felt indirectly, through doctrine and diplomacy rather than spectacle. The world lived with their implications without witnessing their manufacture. In Germany, the lesson was absorbed differently. Reconstruction emphasized industrial resilience. West German engineering culture embraced quality within process. East Germany mirrored Soviet production doctrines. Both reflected an understanding born from defeat. Endurance mattered more than brilliance. The V2 faded into history as a technical milestone, not a strategic success. Museums preserved its shape. Textbooks recorded its achievements. But its philosophy did not survive. What endured was the system that replaced it. By the time rockets carried satellites and astronauts, their origins in terror and desperation were largely forgotten. The assembly line had normalized them. What once astonished now proceeded quietly, governed by checklists and tolerances. And in that normalization lay the final aftermath. The transformation of rocketry had reshaped warfare, industry, and human responsibility, leaving behind not ruins, but routines. Routines powerful enough to outlast the war that gave them birth. If you'd like, we can now bring the story to a quiet, reflective close. The story of rockets after World War II is not merely one of technology. It is a story of philosophy, of process, and of human adaptation. What German engineers once crafted as masterpieces of ingenuity became, in America, instruments of repetition, endurance, and system. In the desert of New Mexico, in the factories of Alabama, the first assembly line rockets embodied a quiet revolution. They taught a lesson that transcended warfare. Brilliance alone is fragile. Only structures capable of sustaining, reproducing, and absorbing failure endure. The handcrafted perfection of Peenemünde, for all its ingenuity, could not match the relentless certainty of a line of missiles rolling from production to launch. For the engineers who had once been elite, the experience was humbling. They confronted a truth both practical and philosophical. The future belonged not to individual genius, but to systems. Their knowledge remained vital. It was reframed, codified, and multiplied. Personal mastery was replaced by distributed competence. The human imprint survived, but it no longer dominated. That shift reverberated far beyond rocketry. It influenced Cold War strategy, industrial policy, and even the morality of weapons development. Destruction became programmable, measurable, and repeatable. Warfare became less about singular moments of heroism or ingenuity, and more about preparation, redundancy, and endurance. And yet, amid this mechanized certainty, the human element persisted. Curiosity, expertise, and courage were still required to design, to innovate, to adapt. The system absorbed mistakes, but it could not replace insight. The rockets were ordinary, but the people behind them remained extraordinary. In the end, the shock that German engineers experienced in America was not a failure of skill, but a confrontation with a new paradigm. The assembly line had become a weapon as formidable as the warhead it produced. And in that quiet transformation, the future of warfare, and perhaps of human endeavor itself, was irrevocably altered. The lesson lingers. The hand builds the first step, but the system carries the journey forward. And from that journey, history learns not only what was made, but how it was made and why it mattered.